Hi, this is a video editorial for the LeetCode Weekly Contest 504. I'd say the problems this time were decent, like Q4 was on the easier end, but I found Q3 quite enjoyable. Q2 was alright as well. So I'll be going through the problems in the order of their appearance, and I'll share how I implemented my solutions. I'll explain my implementations, which I did during the contest, and after this, I'll attach the live solve section where you can see how I approach the problems in the live contest itself. So Q1 was straightforward as expected since it was a three-pointer. Basically, for an integer, we had this sum defined, which was the digit into the frequency of its count over all distinct d, and we have to return the score, right? So like this is you could either simulate this using a map or something, but if you observe, this is basically just the sum of all the digits. So instead of doing all this, we can also do this. Uh, One second. This would just sum all the digits and return that. So this works for this problem as well, and the implementation is way shorter. Moving on to Q2. Q2 was like harder than usual Q2s, but it was still like, if you know some concepts, it's straightforward. Basically, we are given an array of items where we have the factor and its price. And for Q1, the number itself is still 10 power 9, so this will work since that means at most 10 digits. So this is O of 1, O of 10, O of length, log base 10. For Q2, we have this array items where we have the we have the factor of the item and the price of the item, and we have some budget, and we have to find the maximum number of items we can buy within this budget. So this is kind of an abstract setup, right? But we have, for every item, we have unlimited copies, and like for the first item we buy of every type, we can get free copies, and free copies have to follow this rule. Basically, J can be a free copy of I if we are buying I for the first time, obviously, and the factor J is divided by factor I. And this was the second point. Basically, this basically restates what I said before, that we get free copies only when we buy it for the first time, right? And the same item can be gotten, we can get the same item for free via multiple eyes. And the most important thing here were the constraints, and the length of the items is less than equal to 1000, the budget is less than equal to 1500, right? So basically, like, we can do some sort of knapsack here on this n cross budget, but how do we handle the free items thing? So what I did was, let's say we are at some index I with some budget remaining x, right? Either we buy I or we don't buy I. That would be the regular knapsack, right? So if we buy I, we go to I plus 1 comma x minus y, where let y be the cost of I, right? If we don't buy I, we go to I plus 1 comma x, right? Since we didn't buy, the budget remains the same. 1 second. But here we have unlimited copies of I, right? So we can buy multiple of them. So instead of running a loop, which can increase our complexity, what we can do is, if we don't buy I, we just don't buy it, right? So we go to I plus 1 comma x. But if we buy I, what we do is, we transition to I comma, 1 second, I comma x minus y. This basically means that we have bought one copy of I and we are still staying at I to see if we can buy more I's. Like if we buy more I, we'll be here only, else we transition to here. You can think of it like a sort of graph, right? So this graph would be like this. We are at this point. Either we buy it again, so we loop back to here, but with lesser budget, which, since we have bought it one more time, right? Or we go to the next node. So this will work like this. But now we also have to keep a track, since if we are buying something for the first time, we get free extra copies, right? So we can keep another index here, like let's say f, which stands for if we bought it for the first time. So if we are transitioning to I+1, the f value would be 0 as well. But if we do this transition, the f value would always be 1. And using this f value, we know if we are buying it for the first time or not. And if we are buying it for the first time, we can add the extra free copies. And since n is less than equal to 1000, we can compute the free copies using a brute force only. So this was my solution. Basically, this is me just resetting the DP matrix. This is extra, which states how many extra copies of how many extra copies of j I get with some I. And this is the computation, and this is the recursive call. So here, either we don't buy it. If we don't buy it, that means we haven't bought it before. This is always 0, I+1 and same budget. Else, if we can buy it, we transition to, since we have bought it one time, we do this +1. Since we have bought it, this is always 1, and then budget minus item size. We remove the cost of that. And if we haven't bought it before, then we also add the extra ones here. And yeah, this was the DP. I had some implementation mistakes, which is why it took me slightly longer than it should have. Like, I had this idea fairly quickly, but implementation mistakes were a theme this contest. So this was Q2. Q3 has kind of the same setup, but the difference is we have this budget and price are less than equal to 10 power 9. Factors are less than equal to 10 power 5 only, n actually, but and there was also one, like I usually for these like two-parter problems, I usually solve them together, but here there were some other difference as well. I think it's likely the same. Okay, so we'll see. I'll see any differences if there are any. First of all, the obvious difference is in the constraints, right? But I want to see if this would pass here. Curious. Yeah, okay, so there's some other difference in the problem. All right, never mind. So if going through the problem statement again, we have unlimited copies, the items and the budget that remains the same. But we have this: for every purchased copy of I, it can give me at most one free copy of another J. It does not give, acha, haan, yeah, the difference was this only. We receive one free copy of every J, right? Such that this rule is followed. Here, with every I, we only get one free copy of a J. So this is how the problems are different. And the satisfiability should be the same only, such that it is factor I, J is divisible by factor I. And this every ordered pair can exist only one, but the same item can be received from different I's, right? Obviously, we can't DP here since we have this. The constraints won't fit for the budget into anything, but we can make some observations here. First of all, we only have to maximize the count, right? So let's say we have, if there were no free things, we had two items. One was, let's say, of some cost 5, and one was, let's say, of some cost 3, and we had some budget, let's say X. It's obviously better to buy the cheaper one, since X by 3 is always greater than equal to X by 5. This would be equal to because of some float shenanigans, but usually this is the case, right? So here, buying this will always be better. So like, once we have exhausted all of our free items buying things, we can try using this idea, right? So now we have to think about how do we exhaust the free items. So for the free items, my thing was, let's say I have some price pi, price I of some item I with some factor I, right? And this factor I allows us to buy some at most k more items. My bad. Let's say this factor I allows us to buy some k more items, right? The different ones. So for these k items, this is basically, since we are getting these for free, it basically means that we are buying 2 items at once. So we'll have some pi, we'll have, 1 second, we'll have some I with some, 1 second, let me visualize this better. We'll have I with plus this, I plus this, I plus this, and I plus this. This means for these items, if we are buying 4, we are actually getting 8, right? So this thing was a idea which I had. So for this, let's say like somehow we can get this count very quickly. We'll see how we'll calculate this later, but let's say we can get this count very quickly. So I have some budget X, let's say X remaining. Now I can buy budget if I'm buying this for the first time. Like I'm trying to exhaust all of the items for the first time, right? I can obviously buy, and it's 1 second. Its cost would be BI. The cost of the current item is BI. Nah, PI, right? Yeah, PI is already the cost. So I can buy X is the budget, right? My bad. I can buy X by PI items. That is already an upper bound, right, on the number of items I can buy. And even with this upper bound, how many the free ones I can get? It is bound by K, right? So we have min of K comma X by PI. These are the items I can get twice of. So this would be into 2, because I'll get X and I'll get the PI itself and the ones I'm getting for free. So this would be the case. And since here I'm getting 2 items instead of 1, the cost for every item would be PI by 2, right, instead of PI. So, and here I can basically, so my idea was for every item it would exist in a PI state and a PI by 2 state. I'll sort based on these. I'll get the lower one first, the small, since let's say this PI was, let's say, some 100 or something, and we already have some item which we can buy for 5, so it's always already better to buy that, right? So what I did was I sorted every item based on PI and PI by 2, and I went from the end. Now basically I went from the best one. I checked if it was of type 1 or type 0. Type 1 is basically it refers to the fact that we are doing this operation, the one where we are getting other items for free as well. And type 0 is the one where we have already exhausted this operation, so we have to do this. So after sorting, it was just doing this math and adding stuff. So this was my implementation. And yeah, one more thing. For getting this count, I stated we have to get this count, right? For this count, we can use the harmonic sums idea, where first we mark every factor frequency, and then for every factor we create some other array, let's say H, in which we do the harmonic sums iteration. So here max F is the max possible factor value, H has the harmonic sums value of frequencies, right? So here I'm doing this, but this will also include the value of itself. So here in the calculation I'll subtract it by 1. Here I'm creating the array by adding both 0 and 1. 0 is the state where we have already bought it, and 1 is the state where we are buying it for the first time, which means we are doing this operation. And then this is just the sorting logic. I sorted it in the reverse direction, so I can do this pop back thing. I get the index and the type. I get the factor and the, what is this? The price, yeah. If it's type 1, then we do this extra possible thing is this only. This min of budget by cost, and the extra possible. Here I'm subtracting by 1 because it will include itself as well. So we have to remove that to get this, and then we do this. We are adding 2 into count, since obviously this will fetch us one free one. Else it is just and we subtract them from the budget. Else this is the other variation where we can buy multiple, where we have already bought stuff, so we can only do a simple buying operation which fetches 1. So it is just this, and at the end I'm just resetting my frequency and harmonic sums array. So this was Q3. I like usual harder than the usual Q3, but I like this problem. And Q4 was, I'd say, kind of interesting. Basically, we are given an array nums and we want to reconstruct array result by repeatedly performing the following operation. Like we choose a integer k such that k is between 1 to the remaining length. We compute the max of the first k, we append max to result, and we remove the first k. Now we have to return the lexicographically largest result, right? So my first intuition was, since we are doing some lexicographically largest thing, we can maybe apply greedy, because lexicographically largest means like if we have two options, we can somehow make this larger. This is the result, right? This is index 0, this is index 1. If we can somehow make a earlier index greater, it would mean that the output is lexicographically larger. So this was my sole idea here. If it is possible to make the current max larger, I would always do that. And if it is not possible, it is always optimal to end it early, because it will allow us to increase our string size, right? So if we have some a and let's say some other characters, any other a, and here we just have a. So this is lexicographically larger because it has a large string, right? But if we had this for b, this would be lexicographically larger. So this was my implementation idea basically, and my implementation just supplemented this idea, where I kind of simulated this only. For every value, since and the constraints obviously were n and x less than equal to 25. Even if x were larger than n, then we could just let's say x was less than equal to 1e9. We could ignore values greater than n plus 1, because those would never be a part of max anyways, right? So in my implementation, what I did was I tracked the indices of every value. And now since we have to choose k at least 1, I'm performing the k at least 1. I'm setting the current max based on the k, right? So here, and this is a set of the current elements I have, and this is the current max I have. I have to choose k equal to at least 1, so I've done that. And now if there is some index which has this max, I'll set that as my target. And I'll go to that index. While going there, I'll remove these values, since those will get eventually removed. And then after that this operation is done, I'll increase my max. And this is repeated while the operation stops. And this, even though it seems like it's a triple nested loop, here all of these loops are moving this st pointer ahead, right? So every st gets activated upon once, and this works. And at the end, I'm pushing back max to my answer, and I'm returning the result. So like the explanation of this problem was shorter, because this is just like implementation idea, right? Like I want the earliest index I. Actually, like this is also not required. You can use the vector instead, but I'll leave that exercise to you. All right, so yeah, these were my solutions for the problems. Overall, I felt the problems were like of nice quality, like especially Q3 I liked a lot. And after this, you can see how I approach these problems in the live contest itself. All right, bye.